Hi, everybody. This is Edmund. I hope you're back from lunch. Igor, if you're on the call, I think you are, feel free to take over and start your presentation.
Yeah, I'm here. So please let me know if you can see my slides. I'm sharing my screen again.
Yeah, we do.
Okay, great. So it's me again, and now let's talk about next quite natural part of our today's talk. So since we talked about DPC++, SQL language and basic concepts there, it also makes sense to talk about the tool we provide to developers, which is significantly reducing the amount of work to migrate existing codes to DPC++, right? So, and this tool called Intel DPC++ Compatibility tool. So we'll have a short overview of what is it and how it can be used. And I will also show a couple of examples like basic vector addition, since we talked about it in the first part, and more or less complex project compared to vector addition, because everything is relative. So more or less complex project migration of Rodinia code. Again, I really want to have this session in a more interactive mode. So if you want to ask questions during the presentation, I will greatly appreciate it in any way in the chat or by just interrupting and asking me a question. Okay, so obviously when the SQL was introduced, actually hundreds of thousands of developers were already using our technologies, our programming models, and obviously it's clear that CUDA has a very wide adoption and is one of the most common standards nowadays for heterogeneous programming and GPU usage in heterogeneous environments. So it was obvious that to allow users to understand and try all the benefits of SQL, we need some kind of a tool which may help to easily migrate the code from CUDA to SQL, right? And that's why this tool was introduced as a part of OneAPI toolkits. So it's available in OneAPI based toolkits. And the idea is that you are taking your CUDA source code, you are passing it as an input to your compatibility tool, as well as CUDA header files, because this is enough to understand that that all your sources are compilable, right? Including some additional include header files and so on. So everything that the tool can recognize that, okay, your CUDA code is valid, right? This is important, and I will reiterate it a couple of times because this is the way how the tool works. So you pass your CUDA source code plus additional header files or whatever to make sure that the code itself is correct. And the tool is trying to migrate step by step, depending on the way how you call it. It may try to migrate the whole project, standalone files, but it's doing the migration of the kernels, including macro definition and all that stuff to corresponding SQL code. And it's doing it quite well. So the initial goal was to do a migration of 80–90% of the code, which usually can be migrated automatically. So which means that no modification required there, but the tool not always can do it, right? So there are some corner cases where it's not so easy to map something, or it's not clear. So like the developer should decide how better to do my migration. That's why there will be always some portion left, right? And I know that there are open source projects now happening which are helping to further fine-tune the migration, so to make it even closer to fully autonomous migration. But again, it's not happening right now. And once you're getting the skeleton of your code, right, then you are carefully reviewing all the warnings from the tool, taking into account messages where it not always errors, but it's quite often advices on what you better to try, right? and then you need to fine tune your code and go further with the next steps. So in principle, the way how you work with the tool consists of 3 steps, right? So one step, which is preparation step, is actually not always required if you are doing one file migration and you know which compiler options were used for your original CUDA code. So imagine you have a project which was compilable with NVCC, right? So it was compilable and runnable on NVIDIA hardware. So now you want to migrate it. So you want to pass to a tool not only the source code, but also these options which were used. For example, if a standard C++ standard were used different from C++ 98, then you can specify it additionally. Or imagine in your source code you have some macro definitions, right? And you need to keep this in mind and also pass this macro definition to the tool so that it can recognize the code precisely like like it was when you compile it with the CUDA. So it helps a DPCT to understand that the code itself is valid, right? And you can do it in different ways. So actually, all you can do is you can just invoke the tool with this command DPCT, and in that case, the tool will try to migrate the file you are passing to it. But it depends. It depends how tricky was the initial compilation of the code with NVCC. So that's why usually we know that existing projects were quite heavily using make or CMakes, right? But finally CMake generating some kind of make files. And that's why if you have a make command, what you can do, and it's a part of a bundle of DPC++ compatibility tool, there is a tool called intercept build, which allow you to intercept all the compilation commands which are used to compile your original CUDA code by NVCC. So it just parsing your makefile. Actually, real compilation doesn't happen here. What the tool does, this intercept build tool, it parses your makefile. It emulates this execution, but it doesn't really perform the real compilation. So it's just taking all these commands, all these flags and location of the sources, and it creates so-called compilation database file. So this file with a in a JSON format. And by doing that, you can give the DPCT tool the knowledge about all the hints and tricks which were used in the initial project to compile your code. So it can gather the data on where to find the correct include header files, where the files allocated, and so on. So this is quite important step for existing projects. And I sometimes while working further with a tool, it sometimes may be finally required to try to migrate a single standalone file. And what you can do in this case, if you intercept it with compilation database, is, for example, you can take a look on this file and you can find all paths and options used for compilation of a specific file, extract this and pass to the compatibility tool so that the tool knows all macro definitions, headers, and so on. So this is quite some kind of a BKM or a hint which you can try. Because for large scale projects, the tool from time to time may generate quite many errors, and it's sometimes better to switch to file by file migration process. And on the third step, you need to verify the source. So it's still a mandatory part that you are taking a look on your code, checking the correctness, and fix not migrated part yourselves, or modifying the code which warns you, okay, like just think about it, that initial CUDA code may be very fine-tuned for NVIDIA hardware, right? For sizes of blocks, sizes of grids, and so on. And let's say if you will run this code on Intel hardware, for example, there these settings may be different. So it's why sometimes it's important to change these hard-coded predefined sizes of problems, right? Sizes of settings for the hardware in the code. So this is what the tool cannot do for you, right? You should know where you're going to run it. As I said, actually, SQL nowadays support the execution on NVIDIA hardware and on AMD. So it's quite common pattern that the developer takes existing CUDA code, migrates it to the tool, doing a bit of modification and fine-tuning of the code, and then it's possible to run it back on NVIDIA hardware, but also on any other hardware. So it's releasing these limitations or bounds of where you can run your code. And this is, I guess, one of the main advantage of a SQL itself. An obvious question will be how efficient this mapping can be done, right? So think about it, that what is happening for the code. So on the left-hand side here, you can see a simple vector addition sample written in CUDA, where you have a kernel and you have an invocation of this kernel and allocation of memory and memcopy operation, right? So this can be quite precisely mapped to the SQL code, and that's what the tool is doing by migrating it step by step. I want to highlight a few important points here. So first of all, the mechanism of how a device is picked up is different, right? Of course, because we are abstracting on any vendor. That's why we have this in SQL, there is this queue mechanism, right? Which we talked about earlier. So in CUDA, it simply doesn't exist because it's obvious it will be runnable on some NVIDIA device. So since we are not locked to this, we have an option to decide where do we want to execute. But since we are mapping the CUDA code to SQL code, we need to get some kind of a default behavior, right? So what's happening is we are getting some kind of current device. So there is an API in the DPCT namespace, and this is important. So it's not a SQL namespace, but it's some kind of additional namespace introduced to the tool. And we are getting the default queue from this DPCT device. So be very careful. I want to warn you. And that's why I highlighted in yellow background mode here, that each time you use some classes or APIs from DPCT namespace, you need to clearly understand what these APIs are doing. And I will show on the next slide why it is important. The main idea of these APIs from DPCT namespace, and they are usually called helper functions, it's some kind of a glue layer or a bridge between CUDA and SQL, right? So not always it's possible to map one CUDA API call to precisely one call in SQL, right? That's why DPCT has some kind of wrappers to get the similar functionality sometimes, or to provide some additional functionality which is not yet in the SQL standard itself. But the intention of the tool is to try to generate the SQL conformant code as often as possible, right? So you can see here that it's not DPCT malloc allocation functions. It's standard malloc device allocations from a SQL, right? And it's the same, it's like range and other classes which are used here, they are coming from the SQL. So this is SQL standard features, as well as memcopy and other stuff. But there will be from time to time the requirement for these additional interfaces or wrappers from DPCT namespace. And that's why this include header file is required to compile. So it's finally not 100% SQL code, right? So it has an additional requirement for header files. And you can use these header files from the tool, and also in the last releases of the tool, on the demo part, I will talk about it in more details. we introduced a new option which actually even help you to generate this header file. So because by default you need to gather a full set of header files from the tool, but actually you're probably using only a few features, right? So the tool can actually generate for you the subset of the header files which you can use for your project, and it's quite useful. Any questions here? Okay. And this is one example, why paying attention to the DPCT namespace makes sense. So in the previous example, you've seen that we were using the default queue, right? The default queue member function from the device external class. And you can see here that this default queue is actually returning some data from this class, right? But now let's take a look on how it's actually constructed, how this device extension class is constructed in DPCT namespace. And you can see here that if this macros is not defined, and by default it's not defined, we constructed the queue with a property called in order. So what actually this line doing is it's constructing the in order queue, which is not, let's say, which is quite good when you are migrating from CUDA to SQL, because in CUDA the execution is synchronous, right? So all kernel invocations are synchronous, but in SQL by default they are not, and that's why this implicit setting, which is used for the queue, really makes sense by default. But it's not, let's say, then you will finally share this code with someone else, and if it will be not clear how this code was written, right? It may be quite tricky to understand that actually all kernels in this migrated code will be executed one by one, right? Will be executed asynchronously actually, but one by one. So the graph will be always non-parallel, let's say this way. And if you don't want this, you need to override. So again, this is some kind of a default behavior. It is quite often recommended that you create your queue as you want, right? The tool is just getting some default device and default queue, and it's better for you to override this. So this is what the tool is not able to do itself. It's just one example. So there may be other example. The other example is, okay, I showed you how the queue was extracted, right, or constructed. The question is which kind of device the tool is going to pick up. It may be also tricky because it's also going from DPCT namespace. So just keep this in mind. Is to understand the behavior of your code, you need to understand which APIs you are using. And if these APIs are not coming from a SQL standard and coming from the tool, then you can go and check the implementation. It's really recommended from my side. But it's like I highlighted the basics which I hit. I haven't seen so many deviations with the standard SQL behavior for the code generated by the tool. It's just really corner cases which you need to keep in mind. Now, if you best known methods for you on how to do the migration. So what I'm usually doing is, since you're coming from CUDA, right? Sometimes it makes sense to double check that your initial CUDA code, it's actually compilable with CUDA tools, right? With NVCC, for example, and double check that your project is compilable with the original Makefile project. And only when you double checked, then perform the make clean command. So this is important for the tool. Before you are doing intercept build, you need to clean your existing project. This is quite important. Developers are missing this step, and then the intercept build intercepting a wrong sequence of commands, right? So then try to intercept this project right? And compile. And if you generate, if you're facing some issues, then just what you need to do is on the first file, there's some kind of unexpected behavior is observed. You can just check your compilation database, check the options which were used initially in the initial project for the CUDA code compilation, and try to run the tool on this specific file. So just to check what's happening with this file. So this can be quite important. And as I said here, it's quite important to make sure that DPCT recognizing this CUDA code as a valid code, right? Because what's happening is that the tool is actually checking the correctness of the syntax, right? It's building the syntax tree, and it's trying to understand if the initial CUDA code is actually valid, if there are any syntax errors there, and so on. So that's why it is important to do this like initial check with NVCC and then the check with DPCT to understand that it's recognized equally, because sometimes it may be the case that it's not. And then you need to do maybe to add some macro definitions or some include paths are missing and not passed to DPCT. Or one example is maybe the default C++ standard you need to specify for DPCT so that the tool knows that the input code is actually using some C++ 11 features and not default C++ 98 for CUDA. I just want to show that the migration already happened for quite large number of codes, and it was quite successful, and in many cases quite big portion of the code, like 95 and more percent, were migrated automatically with the usage of a tool. And one example is this migration of open source EasyWave tsunami simulation code, which was done by Zuse Institute Berlin with a close collaboration and support from our side. And this is a good example of a code where after migration of a code, we were able to run this code on all Intel architectures, including CPUs, GPUs, FPGAs, as well as on NVIDIA hardware with a quite reasonable performance. So the deviation, like performance drop versus native CUDA implementation, was in the range of 5%. And we run it actually on different CUDA devices. So not only P100, it was also our like V100 and so on. And we just recently ran this code even on AMD GPU. So since I said that in the open source project, we now also support AMD GPUs as well. So this giving us almost unlimited set of hardware vendors we may finally use to run our SQL code. So it really makes sense. And again, the performance may be quite promising. And you need to understand that when we are migrating CUDA code to SQL, right, like doing this stuff, and then we are compiling then our SQL code and running it. I was talking earlier in the previous session that finally this abstraction, right, SQL abstraction, goes down to a lower level API. And when we choose CUDA backend, then it will go to CUDA runtime. So it means that this high level code under the hood will map to something similar to CUDA code. So, and you can actually even use NVIDIA profiling tools for this SQL code, and you will see same CUDA malloc or CUDA memcopy operations. Again, because this is how SQL is implemented. It's by standard. Since it is abstraction on the lower level, it should map to some kind of lower level API. If we will use OpenCL, there will be OpenCL API calls. If we run it on NVIDIA with a CUDA backend, there will be CUDA APIs. So, and when we're talking about the performance portability for this stuff, right, it's quite important how well this migration happens, right, and how well this migration from abstracted SQL code to a lower level backend API implementation happens. And if it's quite efficient, and it is in many cases, then you will probably get the similar performance like you had in the native CUDA code. But it really depends on the workload. So first of all, it depends on this step, right? So how efficiently and how good we can map CUDA APIs to SQL APIs, because if let's say some intrinsics are used in CUDA code, there is no simple way to map these intrinsics to SQL, right? SQL doesn't have this level of implementation. SQL is an abstraction or something. So, and in this case, this will be a bit tricky to do this. Any questions? Okay, so now I want to show you that this is a link. So again, I keep collecting for you some useful links on almost each slide. And here you can find this link to a recording done from a different workshop where engineers from ZIB were presenting their work, and even more, it was also hand exercises on the migration of this tool. So I really recommend to watch this recording and follow the steps there. It's quite interesting on the open source project. And my intention for you is to show you the usage of a tool. So I will do it in the dev cloud, but you can also do it on your machine. So you just need to get the base toolkit. One important note is that to start the migration, you will need to have a CUDA header files available, right? So if you have your CUDA, and obviously, if we're talking about some developer who is going to migrate the code, it usually means that he has this code compilable and runnable on some machine, which means somewhere he has CUDA SDK installed. So all you need to do is just grab include folder, right? Folder with include header files from that machine and reuse it on a machine where you are running the tool. The useful thing is that if you're doing it on the same machine where you already have CUDA SDK installed, then you don't need to do anything. So the tool is able to recognize the default location in user folder, and by default it will use the CUDA header files searchable in this default location. But if you're running it somewhere else, let's say in my case, I'm going to show you how I use it on the dev cloud, then you need to upload headers there. So if you're going to follow these steps after the presentation, then these are the prerequisite steps on the dev cloud. So it's just to clone the samples and go to the special samples dedicated for the DPCT and migration of the code. So let me first show you the basic idea what I want to show you, and then we will switch to a Jupyter notebook with an open terminal, and I will go over all these steps as well. So it's basically to show you the migration on quite simple vector addition code again, and this is how I am passing the path to the include header files, right? Again, on machine with installed CUDA SDK, you don't need even to do this. And then the tool providing you some output. So I intentionally run it with all default settings except the path to CUDA header files, because in this case, the tool will create for you automatically a DPCT output folder, and this is where the tool will put the migrated code. And it's providing you messages, right? Diagnostic warnings. And by going to this link, you can get a full and complete list of these warnings, including advices what you expect it to do. So this is quite convenient. And okay, then you can go to the location of this code and try to compile it further. So it is, in this simple case, the migration was done 100% automatically, right? There is a way how you can control the code generation by the tool, right? For example, you can enable or disable the template deduction rules for the tool. So let's say if by default there may be this kind of code generated with implicit or explicit instantiating of a dimension for the ND-range class and for the range class, right? Then if you enable CTID, then you can see that the code which is finally migrated, it's using this CTID feature. So this is quite useful, and you have a control of this. One code I'm quite often using as a debugging step, right, to understand what was mapped to what, instead of using, let's say, some kind of a merging tools or diff commands which can highlight the differences between the codes. You can use this keep original option, right? And by doing this, the tool will add you in the form of comments the original CUDA code, and after that the corresponding code generated by the tool. This is also quite convenient to see how the CUDA code was mapped to a SQL code, right? And then we will go into more details about the Rodinia project. So it's a bigger project with more files. It's still relatively simple. I mean, just a few files, but the idea is to show really how this intercept build command looks like, and how you can do a migration for the codes which has make files. And as you can see here, since it's more complicated code, there were more warnings, and in this code it was a requirement actually, because the code was not compilable out of box. It was a requirement to modify the code. So okay, let's now go to the terminal. So again, it's very simple to get to this point. So you need to register on the dev cloud, click try in Jupyter here, and it will open you this stuff, and just clicking this new launcher allow you to select what you really want, and you just need to click on the terminal, and it will open you a terminal, right? And then as you remember, I was playing a bit with the settings here, right, with running different commands, but you need to, don't forget to get the node in the interactive mode, right? So because now I'm not on the login node, but I'm on a compute node, and I got this interactive node by using the command. It is listed on the slides which are shared with you from my first part of the talk. So let's first just check if we can invoke the tool, and we actually can, and what kind of features we actually have with the DPCT. So here you can see that you have a long list of options you can use in order to control the code generation. So I just showed you this enable CTID, right? Template argument deduction, which is off by default. It's one stuff, but you can do a lot. So you can actually reformat your code. So if you don't like the formatting of your initial CUDA code, you can follow different coding styles. You can also, as I showed, keep original code, so it's add as a comments to the generated code. Now the tool is developing in the direction that you will also have a way to control which kind of DPC++ extensions may be used, or experimental features. And so you can force the tool to strictly follow a SQL standard, or to allow the tool to use some DPC++ extensions which are not yet in the standard. So depending on your final goal, because if you really want finally to get the code running on all variety of hardware, then it's better to avoid some extensions. But if you want to fine tune for Intel hardware, then the usage of DPCPP extensions really makes sense, because you can use some kind of features which are not yet available for different backends. What else is important is you can control the way how the tool works. So if there is a parsing error, then you can enable the mode when the tool will immediately stop once it's getting the parsing error. I talked during the previous presentation that actually when you pass the lambda to parallel for method, right? You're allowed to not give an explicit name for this lambda. So that's why so-called SQL unnamed lambdas are used, and the compiler generate the named lambda itself. But you can actually force the tool to generate kernels with the kernel name, which may be important in your case. Again, I said that there is a way to control DPC++ extensions. There is also a way to control experimental features. So we have this separation at this moment between extensions and experimental features, and that's why we have this separation in the set of options you may use. Yeah, that's it. So I don't want to go into all the details here. You can control the dimensionality of a default range, because by default it's usually using 3D ND range. And if a code was only 1D range, you will always see 1, 1, and then the dimension of the last, the size of the last dimension will reflect corresponding one-dimensional CUDA code, which is not always nice. So sometimes you can switch to one-dimensional default code generation. What I liked recently is the tool also has this new option which allow you to build a script file. So if you already had a make file and you are migrating the project, the code will be migrated, but there was a responsibility for the developer to rewrite the make file to finally compile your DPC++ or SQL code, right? Because the original make file was using an VCC and was using CUDA source files to compile it. So there is now a way for the tool to generate you automatically the make file as well. So it's just a quite a relatively new feature. I tried it. It does quite good work, but you may still need a bit fine-tune the generated make file, which is by default is like this. Okay. Yeah, one thing which may be also important, I was showing you that you may need to pay attention in the way how helper functions from DPCT namespace are used, and the way how a queue constructed by default in the migrated code. So you maybe remember there was a different way how a queue constructed depending on some macro. And this macro definition, let me go maybe back to this. So this macro definition was, yes, this one, DPCT use USM level none, right? So now if you go here, there is an option called USM level, and you can set it to none, which means that the tool will prefer to use helper functions for memory management migration. So it will not use USM explicit mode to control the migration, which is default. So that's why if it's set to none, then we can actually make the queue out of order by default. Because then we will not use a unified shared memory. And if we don't use the unified shared memory, dependency graph will care about scheduling of our kernels, because there will be buffers and accessors generated. And that's the difference. And just more insights on that. So actually, yeah, let's go to the project. I want to just follow the steps from the slides actually, and we can go to Okay. To the test, and then to one API samples. So again, it's a on one of the slides I had this link, and on the slides for compatibility tool, I also have a link to this GitHub project. So it's a repository with a diverse set of different samples, not always for compatibility tool. So you can find many different useful tools there. But here you can see that there are actually 3 samples. One is a basic vector addition, one more sample, and the Rodinia example of the bioinformatic code. So now let's go to the simplest vector addition sample. As you can see, this is more or less similar what we had on the slide, but the thing is that here you can see that there is an error handling, right? And in CUDA, it's not exception based, it's error based. That's why even in principle, this code cannot precisely migrate it to SQL because we are not handling error status. We are not returning errors. We are raising the exceptions in SQL code. So yeah, let me check. I already done this migration before, so that's why I'm removing the default, because I want to follow it precisely. Okay, this is the output of the tool, and you can see that it's actually generating a warning that the migrated API doesn't return the error code, and you may rewrite this code, right? So now, if we go to the output, and we can see the migrated code, and we have the inline warning from the tool on what should be done here, right? So it's definitely doing some kind of basic stuff, right? But finally, the good practice is that you're going through the code and parsing these errors or these warnings, which should ring a bell for you what you need to do. And actually, we can try to compile this code now, right? We can try to compile this code, and if it works out of box, it's just great. So, and you can see that it works, and that's how we can actually run it on this machine, and you can see that it's producing the correct code. So if you want to understand where this code is actually running, you can, as I showed earlier, enable SQL PI trace, and here you can see that it was a level 0 backend used, and it was running on integrated graphics. So we were able to migrate the code which were initially running on NVIDIA written in CUDA. Now we are able to run it on integrated graphics, and you can go further. You can control where do we want to run it. So let's say you can run it on CPU, right? And you can see that now we are running on CPU on the Intel Xeon processor. So this is really cool stuff, because even with CUDA, right, you're not able to run your kernels on the CPU. So with SQL, you can do this. You can not only run it on GPU, but also on CPU. Or you can even go further and run it on FPGA. Okay, any questions at this moment? So I leave to you the option to try, let's say, this additional stuff like keep original code and other stuff. Maybe let me show one example. So the thing is, if you are running the code, right, in a wrong folder, you'll probably get some kind of these errors, right? So what we actually need to folder back and need to specify what we want to migrate. You see, in this case, we are not saying what do we want to migrate, what's the file. Okay, so we did a migration. Now we put the output to our folder, which we specified by using the outroot option. So outroot option actually saying where do we want to place the migrated code. There is also an important option called inroot, and this is an option you specify for a tool where to look for the code for migration and dependencies, like include header files and other stuff. By default, it will use your current directory, where this, actually not current directory, but the directory where this file is located, because you actually can specify here a full path to this CUDA header file. Okay, so and if we go to the test2 now, but now we can actually open the migrated code, and you will see that yeah, so again, this is a migrated code. But in this case, we enabled CTAD, so that's why you can see here that the ranges actually doesn't have an explicit dimensioning, right? An explicit instantiation of the stuff. So when if you run the diff this code and on previous code, then you can see the difference, right? Okay, so this is the basic stuff to get you a feeling of how it looks like on the one file migration. This is quite convenient for the experienced CUDA developers. So if you start to write, so it's not the tool not always used as a full-scale solution to migrate existing code, right? If you have already your CUDA code, it's actually C++ code, right? And you need to migrate the kernels itself and the invocations of these kernels, right? So, and to do it, it depends how large this section of your code, but it's usually hundreds of lines. It's relatively small portion of your code. So you can actually do the migration yourself even, but sometimes you are puzzled how to map this CUDA API, let's say the function call, right? Some kind of CUDA function call to corresponding function in SQL. And that's why you can write a simple CUDA sample, right? And invoke the tool on this simple CUDA code and just check what should be the corresponding API in the SQL. So it's also a way how to use this tool. Okay, so now let's go to a more advanced example, and it's called Rodinia. So it's actually Needleman-Wunsch, relatively naive implementation of Needleman-Wunsch algorithm. And this is a bioinformatics code to align the protein and the nucleotide sequences. So all that stuff from bioinformatics. And you can see here that in this case, the code is a bit more complex. I want to show you what first step I'm making a clean, right? And then I'm performing the operation intercept will make. So once it is done, you can find that there is a file called not really. So it should be a file called compile commands, right? It's a default naming. So this one. So don't be confused by the other JSON file. And you can see here, so again, this is relatively simple project, right? For the real projects, you will have hundreds of these blocks here. But the idea is that the tool is intercepting the compilation commands from NVCC, and it's extracting the directory where the file the file is located, right? And the location where it should look for include another stuff. And so the tool, when you then passing these options to this tool, it knows where to look for it, right? So now I called the tool, and you can see that in this case, I'm using this gathered or created compiled database JSON file, right? And this file will help and guide the tool on the options to use to migrate the code. We are specifying in root so that we need to take a look for header files and everything else in the current directory. And we are migrating to migration folder. And this is now we are getting more warnings, and you can see that some of the warnings, they are really pointing you that you need to fine tune for better performance if you wish. So let's say if you know that there is no access to global memory inside your kernel, then you actually can replace the barrier with a barrier where you specify the local space. In that case, you can get some performance benefit. So, and since there were multiple barriers used in the code, so it generated it for each time the sync threads API from CUDA was migrated to ND item barrier. But other than that, there are also errors that, okay, it's look like we hit the limit of a time, because we're on top of 3 hours now, and now I need to restart the server to keep using this stuff. I think it's done. Okay. So note that we have this kind of timeout which may happen, right? And now I can actually need to rerun the Jupyter notebook. It shouldn't be a big issue. Okay, so we are back. The server is restarted, and I can run the terminal again, and yeah, that's it. So we can go. Yeah. And yeah, you remember, so that we migrated the code, and now the thing is that we need to go to this code and understand what's happening there. And actually, I even used, in this case, I used the generator of a make file. And now let's open the code itself to check for the errors there. So you can see that the code is migrated, and you can see that for the barrier, there are hints that you can actually fine tune for the performance, right? And it's happening in this source file with the kernels itself. There is nothing else here. But for the different kernel, for different code for the invocations of the kernels, right? You can see the code, and actually this is an issue here. So if you're going to compile this code, we will probably hit an error because this is what's happening here. And this should be migrated by hand in this case, because by compiling these, there will be a compilation error that this conversion may not happen. But actually, you see here that it's even doesn't make too much sense to do it like this. So we don't need the version in the integer way because this API returns actually in the string format. So what we need to do here is actually to create a version string, right? And to assign it to this get current device get info. And this is exactly what the tool is saying to you, that version related API is different in SQL. So it doesn't return version in a form of an integer. So now removing this, this, and probably have a way how we print this error, right? Because we don't need to catch it anymore. Your printfs, so we just, so this is the stuff which we need to do ourselves, right? And this probably should be okay. C-string. Okay, let's try to compile it now. So if we check the makefile, right, we can see that now we just copied. So in this case, I haven't used the option of the tool to generate this automatically. So I just copied this makefile from the initial project, and it's using NVCC. So we actually need to replace it to be able to compile the code with DPC++, right? Which makes sense. So what I'm doing here, I'm removing this, or I can actually rewrite this, but finally I'm replacing the command with dpcpp and the files with the migrated files, right? Yeah, and now you can see that oh, okay, yeah. I actually need to create a string class here. Now it makes more sense. And finally, we can compile this code. So there will be some warnings, but you can see that we compile this code and we can actually run this code now. And this is not a naive vector addition, so it's something more advanced, right? Yeah, there will be an error on how you need to invoke it. So let's say with some parameters. So now it's running. So and you can see as usual, you can see where it is running, and it's now running on our CPU device, because we are actually now on the login node. So it's good that I actually have not allocated the additional node, because if we now check what platforms are available, you can see that the only available platform on this node is OpenCL for CPU, which means there is no GPU. And in the default rating of the devices, it's picking the CPU and running. So this is a flexibility which actually the SQL is giving to you, right? It's giving you an option to control where do you want to run. And if you go now to a node, so if you allocate the node in interactive mode where you can run on GPU, right? So now we can do the same, but on the GPU, because we now logged into the node where we have a runtime installed for integrated GPU. So this is quite important for you to understand that each time you are running on some machine, right, which you have not configured, it may be a good first hint to run SQLLS and to check which devices you actually have available, because on this login node, we simply doesn't have runtime installed for GPU, while on this compute node, we do have it. We do have it, and we have both OpenCL and level 0 for the same hardware. Okay, that's it from my side. Now I'm open to questions. Feel free to go to ask your questions and to use the tool and to use SQL, and it's really straightforward how to use it. Yeah. Thank you for your attention.
Yeah, thanks, Igor. I think there were 2 or 3 questions.